Let's move to the second example, which is time shifting. Okay, so time shifting property. Okay, yes. So what does this say? Okay, sorry. Yes, this says let x of t has x of j omega as the Fourier transform. Okay, then let me call the shifted signal as x1 of t, which is x of t minus t naught. So this fellow will have x1 of j omega as the Fourier transform, which is nothing but x of j omega multiplied with e power minus j omega t naught. So if you shift the signal in time domain, what happens in frequency domain here? The original Fourier transform will get multiplied with e power minus j omega t naught. So let us prove this result. Again, it is simple, but still let us prove that. So what is that? We want Fourier transform of x1 of t, and we called it as what? x1 of j omega. So our x1 of j omega equal to integral minus infinity to infinity x1 of t e power minus j omega t dt. Correct? To find the Fourier transform, we have to use the analysis equation. But what is x1 of t here? x1 of t is nothing but x of t minus t naught. So let us substitute that. So you get integral minus infinity to infinity x of t minus t naught e power minus j omega t dt. Now what we will do? We will replace t minus t naught with dummy variable tau. So this implies what will happen? T will become tau plus t naught, and also dt will become d tau. Okay, but what happens with integral limits? T varies from minus infinity to infinity, so definitely tau also should vary from minus infinity to infinity. So what will happen here? Our x1 of j omega would be equal to integral, limits doesn't change, and hence you will get integral minus infinity to infinity. T minus t naught is replaced with the tau e power minus j omega, and t can be replaced with tau plus t naught, and dt can be replaced with d tau. Okay, so this again we can expand this exponential, right? You will get e power minus j omega tau multiplied with e power minus j omega t naught, because integration is with respect to tau. That can be, okay, I'll write down that this is nothing but integral minus infinity to infinity x of tau e power minus j omega tau e power minus j omega t naught d tau. But what is happening? The integration is with respect to tau, and hence what will happen to e power minus j omega t naught? That can be treated as a constant, and hence we can bring that out. You will get e power minus j omega t naught integral minus infinity to infinity x of tau e power minus j omega tau d tau. But what is that integral here? Integral is looking like what? Fourier transform of x of t. So in the dummy variable we replaced the t with tau. So but the Fourier transform is not going to change, and hence the integral is nothing but our x of j omega, and hence this should be equal to how much? That should be equal to, I'll write down a little bit below. So that should be equal to e power minus j omega t naught multiplied with x of j omega. So that's what we have got here, right? So what did we see? X of t minus t naught will have x of j omega into e power minus j omega t naught as the Fourier transform. So that's easy. So in that way we have proved that result. So what will happen? The Fourier transform, actual Fourier transform is multiplied with e power minus j omega t naught. Okay, so let us see this little bit carefully. So let us further do some analysis. Okay, so what did we get there? We got x1 of j omega to be x of j omega multiplied with e power minus j omega t naught. Okay, but if you remember the beginning of Fourier transform, what did we say? In general, Fourier transform is complex, and hence we can write our Fourier transform in terms of polar form, correct? So let me write down that. So this is nothing but modulus of x of j omega multiplied with e power j times angle of x of j omega, and this fellow is again multiplied with e power minus j omega t naught. So this simplifies to how much? Modulus of x of j omega multiplied with what will happen? E power j. So e power, because both are having same base, we can add the numerator, we can add the power. So you'll get e power j times angle of x of j omega minus omega t naught. Okay, so what happened? What happened? Okay, so what will happen? We will see. So if you take modulus now, so you take modulus of x1 of j omega, okay, that should be equal to how much here? So that should be equal to modulus of x of omega. Why? You take modulus for e power j theta, that should be equal to 1. And from this, what is angle of x1 of j omega? Angle of x1 of j omega is this whole term which is in the square bracket. That should be angle of x of j omega minus omega t naught. Okay, so what is that you observed? You observed that the Fourier, if you shift the signal, okay, what happens to its Fourier transform? Magnitude of the Fourier transform is not going to change, correct? But what will change? The phase of the Fourier transform. What will happen? The extra term minus, it will get transformed. The phase of the Fourier transform will change to actual phase minus omega t naught. Okay, that we will write down. This implies shifting the signal. Okay, so shifting the signal x of t, shifting the signal x of t, what it will do? Has no impact on, correct, no impact on absolute value or magnitude. Okay, absolute value or magnitude of Fourier transform. Okay, so magnitude of x of j omega. Okay, but what will happen? But phase of x of j omega, okay, phase of x of j omega will get added, correct, will get added with, only phase will change, that's what it means. Added with whom here? Minus omega t naught. Okay, so because it varies with respect to omega linearly, this we call it as a linear term, okay, or linear term. Okay, I don't say term also, I say it is linear. Who is linear? Minus omega t naught is linear. Okay, so what will happen if you shift the signal? What will happen to the Fourier transform? Magnitude of the Fourier transform will not get affected, but who will get affected? The phase of the Fourier transform will get affected. So how does it get affected? The extra term minus omega t naught will get added to that. Okay, yes. So let us summarize again. What did we get? X of t minus t naught will have x of j omega multiplied with e power minus j omega t naught as the Fourier transform. Similarly, what will be the Fourier transform of x of t plus t naught? You can easily see that this is x of j omega multiplied with e power plus j omega t naught as the Fourier transform. Now if you add these two signals, what will happen? Which property we have to use? Linearity. Okay, so this implies x of t plus t naught plus x of t minus t naught will have what as Fourier transform here? You are adding in time domain, you should add in frequency domain. So what you will get? X of j omega e power plus j omega t naught plus x of j omega multiplied with e power minus j omega t naught. So this should be equal to how much? You get x of j omega common. You'll get e power j omega t naught plus e power minus j omega t naught. So you'll get 2 cos omega t naught. Okay, so x of t plus t naught plus x of t minus t naught will have 2 x of j omega multiplied with cos omega t naught as the Fourier transform. Similarly, what will be the Fourier transform of x of t plus t naught minus x of t minus t naught? Again, we will use linearity property. So what do you get? You get x of j omega multiplied with e power j omega t naught minus x of j omega multiplied with e power minus j omega t naught, and you can simplify this to 2j x of j omega multiplied with sine omega t naught. So that would be the Fourier transform of this signal. Okay.